Include stdint.h and you get types that say exactly what they are. Int 32_t is a signed integer of exactly 32 bits on every platform where it exists, with no argument and no guessing. There is a signed and an unsigned version at each of the 4 common widths, and the naming is completely regular. U for unsigned, then the number of bits, then _t. Use these anywhere the bit width is part of the specification rather than an implementation detail, file formats, network protocols, hardware registers. Anything where a document somewhere says this field is 32 bits. Below those are 2 families people use less and should probably use more. Int least 16_t is the smallest type with at least 16 bits for when you care about range but want to save space. Int fast 32_t is the fastest type with at least 32 bits, which on a 64-bit machine is often actually 64 bits wide, because that is what the registers are. And int _t is an integer guaranteed to hold a pointer, the correct answer to the problem Long could not solve in the last lesson. 2 more that are not about width at all. Size _t is the type of anything that counts bytes or array elements. It is what the sizeof operator gives you, it is what the standard library takes for lengths and counts, and it is unsigned. And it is wide enough to represent the size of any object your platform can create. When you write a loop over an array, or a function that takes a length, size _t is the correct type, not int. Its signed cousin is ptrdiff_t, the type you get when you subtract one pointer from another, which is signed because that subtraction can perfectly well come out negative. And a small but practical detail, to print a size _t with printf, the specifier is %zu, not %d, not %lu, %zu. That z is a length modifier meaning size _t sized. And getting it wrong is undefined behavior that usually prints the right answer on your machine and garbage on somebody else's. Now the famous trap that comes with all of that. Size _t is unsigned, and an unsigned value is never less than 0. That is not a runtime fact, it is a property of the type. So look at the first loop. Start at n-1, keep going while I is greater than or equal to 0, decrement. When I is 0 and you decrement it, it does not become -1, it wraps round to the largest value a size _t can hold, which is something like 18 quintillion. The condition is still true, so the loop keeps running, marching off the front of your array. Worse, I greater than or equal to 0 is a tautology for an unsigned type, so the compiler is entitled to optimize the test away entirely, and may not even warn you. The second loop is the idiom that works. Start at n, and the condition is I post decrement greater than 0. That tests the old value and then decrements, so the body sees n-1 down to 0, and the loop stops cleanly. It looks strange the first time. Learn it as a shape, use it, and you will never write the infinite one. Finally, you never have to guess at any of this, because the bounds are available in the header. Include limits.h and you get a macro for the minimum and maximum of every integer type on the platform you are actually compiling for. int_min and int_max, uint_max for the unsigned version, llong_max for long, and so on through the whole family, following the same naming pattern. The odd one out at the bottom is char_bit, which is the number of bits in a char. The standard permits it to be more than 8. There were real machines with 9-bit bytes, but it is 8 on every platform you will ever touch. And these are the right way to write a bounds check. If you want to know whether a value will fit, compare it against int_max rather than against a 2 billion something number you typed from memory. The macro is correct on every platform, and the number you typed is correct on one.